How many distinct values of x satisfy the floor value of x squared minus 3x plus 2 equals 0, where this notation, usually called the floor value, denotes the greatest integer less than or equal to x. So the first thing that we should immediately notice is that this equation, it looks a lot like a quadratic equation. The only difference is that instead of x squared, we have the floor of x squared. So I'm actually going to split this problem into two cases. The first case is if x is an integer. And so I'm going to use this notation z. This denotes that x is an integer. So for this case, if x is an integer, then the floor value of x is simply equal to x. And for this case, we now have a quadratic. So now we just need to solve the quadratic equation x squared minus 3x plus 2 is equal to 0. Moreover, we need to check that the solutions to this equation are integers, because case 1 specifically requires that x is an integer. But it turns out that this is the case, as x squared minus 3x plus 2, this can be factored as x minus 1 times x minus 2. So the integer solutions to this equation are x equals 1 and x equals 2. Unfortunately, we're not done yet because we need to also check the case where x is not an integer. So for this case, we cannot say that the floor value of x is x anymore. Instead, we're going to look at this expression, minus 3x. It turns out that we can get a bit of useful information from it. The reason why is because if we solve for 3x, we obtain that 3x is equal to the floor value of x squared plus 2. And the important part about this expression is that the right-hand side, floor value of x squared plus 2, this is an integer. So therefore, 3x has to be an integer. Therefore, x has to be some integer k over 3. So given this, I'm actually going to write x, or we're going to assume that x is in the form 3, let's say 3q plus r over 3. The motivation for using 3q plus r in the numerator is because we're going to be multiplying x by 3. And in doing so, we're going to get an expression only involving q and r with no fractions. So with this, and moreover, we can state that r is either 1 or 2. Right, so think of r like the remainder when the numerator is divided by 3. So with this change of variables, we see that the floor value of x is equal to the floor value of 3q plus r over 3, which is equal to q. And moreover, we see that 3x 3x is equal to 3q plus r. So if we substitute all of this into our given equation, we see that q squared minus, in parentheses, 3q plus r plus 2 is equal to 0. Now we know that r is 1 or 2, so we can solve this quadratic by substituting r is equal to 1 or r is equal to 2, and then find integers q that satisfy this quadratic. So if r is equal to 1, if r is equal to 1, then we obtain q squared minus 3q minus 1 plus 2, which is the same as q squared minus 3q plus 1. So if r is 1, we get q squared minus 3q plus 1 equals 0. Now this quadratic does not have integer solutions. We can check this by solving the quadratic using the quadratic formula. We see that there are no integer solutions for q. On the other hand, if r is equal to 2, if I substitute r with 2, then I'm going to get q squared minus 3q minus 2 plus 2, which is the same as q squared minus 3q. So I get q squared minus 3q equals 0. This means that q is equal to 0 or q is equal to 3. Now remember that we defined x to be 3q plus r over 3. This gives us the solutions. X is equal to, by plugging in q is 0 and r equals 2, I obtain 2/3. And by plugging in q equals 3 and r equals 2, I obtain x is equal to 11/3. So I obtained 2 more solutions by the substitution. So we have 2 solutions, x where x is an integer, and 2 solutions where x is not an integer. Therefore, the answer is B, 4.